Now, there is a small concept which is yet to be discussed. So, we are going to focus on the sphere which is sliding down an inclined plane. It's a rough inclined plane, which means it is going to accelerate linearly as well as rotational acceleration will happen. If you recall, I had explained the relation between linear and angular acceleration. A is equal to r alpha. And a similar relation exists for linear and angular velocity. So the relation between linear and angular speeds is v is equal to r omega. But please bear in mind, both of these equations are only valid under a certain condition. And that condition is this is true till the friction is enough to prevent slipping. So the sphere is rolling on the incline, but it is not slipping. This is called pure rolling, which in simpler words just means the sphere is rolling but without slipping. And that is why from this point onwards, if the question gives this information that either the friction is enough to prevent slipping or they directly say that sphere is rolling without slipping, then only we can use these two expressions. And if we go back to the question which we were solving right now, if you look at the question stem carefully, they have specified that the rolling of the sphere is happening without slipping. And if there is no slip, only then we apply these two equations. A is equal to R alpha and V is equal to R omega. And why this is important? Because if you remember the free body diagram of the sphere, we have mg acting downwards, normal reaction, and friction which acts up the incline. Now, please try to recall friction has two types. Type 1 is static friction and type 2 is dynamic friction. Static friction comes into the picture when the object is at rest or at relative rest with respect to the surface. If you want more details, please go back to the notes where we discussed friction and the types of friction. So, static friction will apply on the object if the object is at relative rest with respect to the surface, and then if the object actually starts to move, which means the object starts to slip on the surface, then the friction which is applied on the object is called dynamic friction or kinetic friction. And if you recall, kinetic friction is a constant. It depends on the type of surface. But static friction, on the other hand, is variable. It goes from zero up till a maximum value. And the maximum value of static friction has been given another name. If you remember, that is called the limiting friction. So let me repeat, the friction will start from zero. It will keep on increasing until it reaches a maximum value, which is called limiting friction. And once the friction reaches the maximum value, and in that instant, if you apply even more force on the object, then the object will start to slip, actually moving with respect to the surface. And that is where the friction which is applied on the object is a constant that is called kinetic friction. And that is why in questions of rigid body mechanics, which deals with sphere rolling down a rough inclined plane, we apply A is equal to R alpha or V is equal to R omega only if it is mentioned in the question that the sphere is rolling without slipping. Or they might say that friction is enough to prevent slipping. Now, let me quickly repeat static friction. Let me write it goes from zero up till a maximum value. And that maximum value of friction is called limiting friction FL. And the formula for limiting friction is equal to mu times normal reaction, where mu stands for the coefficient of friction. And this parameter depends only on the type of surface. In case the question mentions that the friction is not enough to prevent slipping or the sphere is rolling but with slipping, in that case, the friction acting on the sphere is called kinetic friction Fk or dynamic friction. And the expression is mu times normal reaction. The only difference is when we are dealing with kinetic, the mu is called coefficient of kinetic friction. In limiting friction, this mu is called the coefficient of limiting friction. And in books and in exams, sometimes mu L is also written as mu S, which is the coefficient of static friction. Let's go back to the same question. We had done part A, B, and C, now part D. The question is state the relationship between the force of friction and the angle of incline. We just now discussed that the maximum value of friction, which is called limiting friction, is equal to mu times the normal reaction. And what will be the value of normal reaction acting on the sphere? For that, we'll have to go back to the free body diagram of the sphere which we had drawn earlier, which is this. As you can see, mg was broken down into two components, mg cos theta and mg sin theta. And remember that step where we balance forces in a direction which is perpendicular to acceleration. According to that step, the normal reaction and mg cos theta have to balance each other. So n and mg cos theta are equal. So over here, let me write n is equal to mg cos theta and the limiting friction will be equal to mu times mg cos theta. But please remember, limiting friction is the maximum value of static friction. It goes from 0 till this maximum value. So there are two ways of answering this question, which asks us to find the relationship between the force of friction and the angle of incline. Approach one is we can write the friction value will be less than or equal to the maximum value. Maximum value is mu mg cos theta. Now, technically, as we discussed earlier, static friction starts from 0 and it goes to the maximum value. But in rigid body mechanics, we have discussed if friction is 0. Remember that case of smooth inclined plane? If friction is equal to 0, then the object, the hoop in this case, cannot rotate. For rotation to happen, we need friction, which means there is a non-zero value of friction which is acting on the hoop, and that will depend on the angle theta. We are going to discuss about that in part E, where they say the angle of the incline is slowly increased from 0, and we need to find that angle of the incline when the hoop begins to slip, which means the friction is not enough to prevent slipping. Coming to part D, this was the approach 1 where we have written friction is less than or equal to the maximum value, and maximum value is mu mg cos theta. So that was the approach 1. Approach number 2 is also important to be discussed. And for that, let's go back to the free body diagram. And for that, let us go to the previous analysis, which was this. A lot of equations are there, but I only want you to focus on this expression. We had finally reduced that friction is equal to m into a, mass of the hoop multiplied by the acceleration. And the expression for acceleration we had deduced to be g sine theta by 2. So friction will be equal to m into g sine theta divided by 2. And that is why for approach 2 for solving part D, we will use that expression F is equal to m into a, and we will put the acceleration expression which we had derived. So we will get m into g sine theta divided by 2. This is the exact value of friction. Remember in approach 1, we discussed that the friction will go from a minimum to a maximum value. Maximum value we know is mu mg cos theta. But what about the minimum value? That depends on the angle theta. Let me repeat, the maximum value of friction is limiting friction, that is mu mg cos theta. Let me write F maximum will be mu mg cos theta. That's a constant. So answer to part D, either we can write friction is mg sine theta by 2, or we can write friction is less than or equal to the maximum value, which is mu mg cos theta. Now coming to part E, the angle of the incline is slowly increased from 0. Determine the angle when the hoop just begins to slip. Now, the question already has given a hint that the hoop is slipping, which means the friction which is acting on the hoop is the maximum possible. The limiting friction, remember mu mg cos theta. And if I go back to the free body diagram, let's again analyze the different forces acting on this hoop: normal reaction, mg, and friction. We have discussed friction depends on this angle theta. Friction was m into g sine theta by 2. But if we keep increasing this angle theta, the value of friction will keep on increasing. And why is that happening? Because if the angle theta increases, sine theta will increase, and F, the friction will increase. So friction will keep on increasing, but it cannot increase forever. There is a maximum value of friction, which is the limiting friction, the mu mg cos theta. In this specific case, if the hoop begins to slip, which means the friction which is acting on the hoop is the maximum possible, which is mu mg cos theta. So let's go back to the free body diagram. In order to find the coefficient of friction, which the question wants us to find, we have to go back to this expression. F net is equal to m into a. F net is mg sine theta minus friction is equal to m into a. Now, since the hoop is beginning to slip, friction in this case will be mu mg cos theta. So in this specific case where they have said that the hoop is beginning to slip, then we cannot apply all these equations because A is equal to R alpha, remember, is only valid if the friction is enough to prevent slipping. So the sphere needs to roll without slipping, only then this expression can be applied. So back to the equation, F net is equal to ma. Let's write mg sine theta minus F is equal to ma. Mg sine theta minus friction is equal to m into a. Friction is the maximum possible, that is mu mg cos theta. So let's write mg sine theta minus mu mg cos theta is equal to m into Acceleration, the expression for acceleration we already derived in part B, which was g sine theta divided by 2. And now let's try to simplify this equation. We have mg sine theta by 2 on the right hand side. Let's take that on the left hand side, and then mu mg cos theta will be taken on the right side of the equality sign. So on simplification, we will get mg sine theta minus mg sine theta by 2. That will be equal to mu times mg cos theta. And if we simplify the left hand side, let's take mg sine theta common from both terms. We will write mg sine theta, and in the bracket we will get 1 minus 1 by 2. That is equal to mu mg cos theta. Now 1 minus 1 by 2 is 1 by 2. So on simplification, let me write on the bottom, we will get mg sine theta divided by 2 equals to mu times mg cos theta. Let's simplify this further. Mg will get cancelled out from both sides. In the question, we need to find the angle, which means we need to make theta as the subject. So what we'll do, we will take 2 on the right hand side and we'll take cos theta on the left hand side. So the expression will become sine theta upon cos theta will come out as 2 mu. Sine upon cos, remember, is tan. So we will write tan theta is equal to 2 mu. And if we make theta as the subject, we will get theta as tan inverse of 2 mu. And this is the value of angle of the incline when the hoop begins to slip. So what's going to happen till the time the angle is 0 and it increases till this value, the friction acting on the hoop is static, which means it goes from a minimum value all the way till the maximum value, which is mu mg cos theta. And once the angle of the incline exceeds this value of tan inverse 2 mu, then the hoop definitely will slip while it is coming down this inclined plane. And this is how we solve questions of this type.